Everybody, very pleased to be here and met some of you already, and it's been a great pleasure. I'm not convinced that this microphone is working very well. If the people in the back can't hear me at any stage during this talk, please wave, okay? Can you hear me now? Okay. This opening slide shows two computers. One is a computer like the one I've got here today, a modern laptop. The other is the first computer that I ever programmed as a schoolboy back in England quite a long time ago. Okay? And what I'm going to do is I'm going to tell you part of the story of how we got from that Ferranti Pegasus computer to today's modern computing. And in particular, I'm going to concentrate on a period in which universities weren't able to use what the commercial computing companies provided, and so universities invented a lot of modern computing, and I was lucky to be involved with quite a few of the interesting projects. I'm going to concentrate on things I was involved with simply because that's what I know well, but of course many people from many places contributed to this story. Okay, to start, we start in the Age of Dinosaurs, okay? The Age of Dinosaurs in this case means the 1960, and here is a dinosaur. It's an early IBM mainframe, Model 360, a very important family of computers in the history of computers. Before telling you about them, let me just tell you a few things about the context. In the early years of computing, and I would say until about 20 years ago, anything you did in computing was dominated by the fact your computers were much too slow, okay? They were very slow, and everything we did was dominated by the need for performance, and on the other side, the huge cost. I'm not going to talk about how many times computers have got more powerful and things like that. Nobody can really understand exponential things. But just one statistics there. In the 1960s, memory cost $1 a byte, okay? So I've got 8 gigabytes in this laptop here. At 1960s prices, that would be $8 billion just for the memory, okay? And that's the sort of context. There's another very important economic fact, that in the early days of computing, there were economies of scale. A big computer gave you much more bang for your buck than several small computers. And this meant that any organization, and I mean companies, universities or whatever, followed the same basic strategy. You bought the biggest computer you could afford, and unless you were a substantial organization, you couldn't even afford that. And then what you did, you created a computer center, and the computer center's job was to find some way to run this computer and share it amongst all the people who wanted to use it. And the sharing had various things that you did. The system software, the operating system, the operations procedures, and often, in many cases, charging schemes. The idea is if people had to pay for things, they would use them economically. Now, these computing centers are a very important part of the story. They became centers of expertise, but at the same time, they became vested interests. And when things started to change, vested interests always resist change if it means it makes them look less powerful, okay? I was in charge of the computing center at Dartmouth College for 7 years and at Carnegie Mellon University for 10 years after that, with titles like vice provost and vice president. And much of this story is about that period. Let me tell you about the 360 and why it's important. The most important thing about the 360 was it was a family of computers. It was a family of computers, large, small, and so forth. And they introduced, and IBM introduced new models steadily. They gave them different names like 370s and so forth. And in fact, today they're still making big mainframe computers in this range. They call them the Z series. And they were general purpose machines. They were designed for commercial data processing and for big scientific jobs. But the important thing about them was because they were the same family, programs that ran on one would run on all of them. And in fact, IBM was very much involved with standardization of programming languages like Fortran and COBOL, and programs that ran, some programs anyhow, that ran on those machines 50 years ago will still run today on a modern machine. This family thing is really important because if you think of the enormous amount of software that we use when we do everything today, if you had to rewrite it every time there was a new computer, we just wouldn't be able to do it. So the fact there was a family of machines that ran the same software, fundamental importance, and what made this generation of computing different from earlier computers. Okay, a few very simple hardware things. In that photograph that I showed you of the IBM 360, in the foreground you may have noticed some reels of magnetic tape. They were the only place we had to store large amounts of data. Nowadays, most modern computers, most laptops have stored data on disks. This is a really modern Macintosh stores it in semiconductor memory, but in those days we stored them on magnetic tapes. We had a few disks just coming in. They were big, slow, unreliable, and stored about 10 megabytes of disk. Okay, so imagine a computer for an entire organization which might have 2 disks, each of which would store 10 megabytes of disk. Input and output. If you wanted to get data into a computer, you had it punched on punch cards, and if you wanted to get it out, the computer had only one way of getting things to you. We'd have a central computer, a central printer, one printer for the machine room, and the computer would print things out. Communications, notice the communications here, none, okay? This was a freestanding computer. This is the first of 4 pictures I'm going to show you, black and white photographs. Each of them shows somebody with their hands on a keyboard, okay? And this is a punch card machine. In these days, if you wanted to get some data into a computer, you wrote it on a piece of paper, okay? So you're writing a program, you write your lines of code out on a piece of paper, you've got data you want to put in, you do that, and you give it to a professional data input clerk, okay? And so every organization had a group of these people, often a big room just full of these people. They were all women, by the way, badly paid, but very skilled. And what she's doing here, she's typing on this keyboard and punching punch cards. Here's a typical punch card. This is an 80-column punch card. Each column here represents a character. The holes punched in the card are a code, so one code will be a letter A, another code will be a number 0, and so forth. And that was the only way to get data into the computer. Okay. These machines, and IBM in particular, built their machines primarily for the big commercial marketplace. And the sorts of things that the commercial marketplace did were different from what we wanted to do in universities. By and large, the commercial marketplace had a small number of big jobs, and you ran them on a schedule, and you had professional operators run them. So today's Friday afternoon, the machine will be taken over to run payroll. And that was the sort of way they thought about things, which is not like universities. In universities, what we have is we have large numbers of independent people, students, faculty, researchers, and so forth. Most jobs that we run in universities are small jobs. There might be, in those days, it might be something that you did for a class, something that you did for a research project, great deal of program development. And above all, though, universities have the tradition that we do our own work. We don't turn to professional operators and say, run our programs for them. And so universities and businesses diverged. And for about 30 years, university computing concentrated on our types of users. And as a result, universities pioneered a lot of things which are now standard in everybody's computing. The term end user computer, by an end user I mean us, okay? We're the people who actually want to do things. And we put our hands on the computer. We do it. And the system we developed for end users was originally called time sharing. When we started getting more than one computer in a organization, universities got very much involved with centralized decision making and decentralized computing. When mini computers and personal computers came along, we were pioneers in making use of them. Distributed computing, when we attached these things to network, and the networks themselves, the universities took the lead in most, if not all, of these areas. And I'm going to say a bit about all of them. First of all, let us look at end-user computing. Here's my second photograph, black and white photograph of somebody with their fingers on a keyboard. This one is very different. It's a student at Dartmouth about 1970. He is sitting at a teletype terminal. And it's a terminal, and when I stress it's a terminal, there's no logic in this, and there's no processing. All this terminal does is he types a character, shall we say the letter A, and there's a transmission line that takes that character, turns it into an electronic signal and sends it to a central computer. So what he's doing, he's sending one character at a time to a central computer. And the central computer, if it wants to send things back, will send a batch of characters which are printed out on that roll of paper, okay? Notice the big step forward, the end user is putting information into the computer and getting information back. Time sharing was the computer systems we used to support that sort of terminal. And a number of universities developed the first time sharing systems. MIT here in New England and Cambridge University in England were two of the pioneers on this. They particularly built systems designed for scientific and medium-scale research users. Dartmouth, that I know best and where I spent quite a bit of my career, was exceptional in that very early on they had the idea that everybody could be a computer user. And they built a time-shared system for students and general academic users. As I say, these systems were called time sharing. By the way, the origins of this talk was a conversation I had with a group of very good students at Cornell, and I used the word time sharing, and most of them had not heard that term. So how many people here are familiar with time sharing? Okay, about half, no less than half. And it's almost, you know, I can tell your age by whether or not you've heard of time sharing. It was the state of the art at the time. Okay. What it basically consisted of, you had terminals, and the terminals would be scattered around the university, or they would be in computer labs. And as a user, you had your own terminal, and you shared the central processor with everybody else who's running. The whole idea was to give you the feeling that you had sole use of a medium-sized computer. Actually, you didn't. What you were doing is you were sharing a big computer with everybody else. So the central processor, the heart of the machine, we used a system called time slicing. So I might have the machine for half a second, and then you would have the machine for half a second. And then you'd be interrupted, and somebody else would have the machine for half a second. And this went on. Of course, depending upon the number of people who were using the machine, I could get fast response or slow response. And then the memory of the machine, the central memory, which was very small, was divided into partitions, and my job would sit in that partition waiting for my turn to get a slice of the computer. In addition, as disk drives became available, we had a central disk store, and the central disk store, one for the whole computer, but each of us would have an allocation of space on the disk store where we could store our data, store our files privately for when we came back again, and there would be a central library where shared programs and shared data could be stored. Sounds really primitive, but it was the state of the art at the time. Few more details about the Dartmouth system. I've said the first things. The communication used telephone lines, okay? Quite often what you actually took was a telephone handset and you put it in a device, a so-called audio device, audio coupler. Communication speeds 10 to 30 bytes per second. I mean, we think anything under 10 million bytes a second is painfully slow today, but 10 bytes a second is faster than you and I can type, which is really the most important thing. Notice the implementation here. System was designed by 2 mathematics professors.
Oh, sorry.
They were statisticians. Well, one of them was. Anyway, John Kemeny and Tom Kurtz. Okay. Every line of code was written at Dartmouth. I mean, every line of code. The device drivers, everything was written at Dartmouth, mainly by undergraduates, okay? Imagine, I mean, taking a group of you, taking 6 or 8 of you and saying, let's write an operating system, okay? I expect you could do it actually, but we're not going to try. Because Dartmouth concentrated on the end user, the student and so forth, they had to make the system really easy for the students to use and really, really easy for the faculty to use. And so they invented a number of things which you'll laugh at that they needed to be invented. First of all, the commands that you gave to the computer, they invented very, very simple command language, something you didn't have to learn. It wasn't like using, what can I say, Linux or something like that. It was something simple that reasonable people could use. So you'd have a command. If you wanted to create a new file called homework, you would type new, the name of the file, homework. If you wanted to run a program, you typed run. Previously, error messages had been codes like XY32 when you looked it up in a book, okay? They put a lot of effort into commands that you could read, like no such file. First help system, I believe, was created then. And very influential, they created a very simple programming language called BASIC, which was designed to be something that beginners with no computing experience could write small and actually medium-sized programs. Notice the line numbers on this. With those typewriter-type teletype terminals, editing is very difficult. So if you type something in wrongly, the easiest thing to do is actually just to type the line again. So BASIC had line numbers, and you simply want to change line 10, you just typed in line 10 again. Okay. During the peak years, these were the years that I was in charge of computing at Dartmouth. The work I've described so far was done by earlier people. At the height of the time-shared system, we could handle about 200 users with pretty good performance, and we had a robust, reliable system. We had excellent programming languages. We used BASIC and PL1. I gather that for your computer science courses here now, you're moving towards using Python for the first course and then Java for higher level courses. We used BASIC for the lower level course, for the introductory course, and a programming language called PL1, but actually, which long dead, but actually quite a good programming language for the upper level courses. We had a large public library of applications programs. That is, that there was a central disk store with programs, data, course materials for everybody to share. So nowadays you use a website. If I'm teaching a course, I put my materials on the course website. In those days, I put my materials in the course library. Because of the large numbers of terminals, communications, the universities became the specialists in communications. Because small colleges could not afford their own computers, Dartmouth provided a service by which we would have terminals in colleges around New England and further away. Aquinas College here was one of them. They had 4 teletype terminals connected to the big central computer because they couldn't afford their own computer. We had early electronic mail. We had online consulting like chats. And Dartmouth was special in that we didn't charge anybody, our users, for using the computer. It was anybody could use it. We called it the library model. Please use the computer. So Universities, we were really way ahead of the commercial world in these fields. Networking, support for end users, and we were the first people to have to face up to questions of system security, because when you've got a university with thousands of people, some of them are incompetent, and one or two of them will probably be there trying to see if they could break into your system, which they did. And it's actually one of the standard books on computer security, which was written by one of our students at Dartmouth, who made his name by a very elegant break into the system many years ago. Okay, the MIT system that I mentioned, it was called Multics. It's very important in the history of computing because they had very strong contacts with Bell Labs, and Multics in many ways is the basis, the concepts of Multics are very much the basis for the Unix operating system, which you now know as Linux, and has been very, very important in the history of computing. Dartmouth's command language was widely used in mini computers and personal computers, and in the film 2001: A Space Odyssey, the robot HAL actually uses commands from the Dartmouth command language. BASIC, because it's so simple, easy to implement, efficient on small machines, was the first widely used language on the mini computers and then on personal computers. So we had a system that we were proud of. It was a technical achievement, and people had done some fine work. But time sharing was not perfect, and there were three problems. And these three problems you'll see again as I talk about other things. One is you provide a uniform service for everybody. And of course, everybody in the university is not uniform. Some people want one thing, some people want another. Second is we never had enough capacity. We never had enough equipment. We never had enough disk storage. And finally, we could only run programs that were written for that machine. We couldn't run programs written elsewhere. The early statistics packages, there's a package called SPSS, which some of you may have heard of. Very popular, very important, but we couldn't run that for our social scientists. So, what came next? What came next were mini computers, okay? This is a digital VAX 11780, Digital Equipment Corporation, otherwise known as DEC. It was very important, and the reason it was important was that in the 1970s, these economies of scale started to break down. And in fact, fairly quickly, they got reversed. So the VAX was a very important computer. It was a smaller computer, but it gave you more bang for your buck than a big computer. If you were a scientist or an engineer with a lot of big calculations to do, you'd do better to run them on one of these mini computers than to pay for a share of a mainframe computer. And there were a whole number of companies grew up to build these computers, mainly in the New England and Northeast United States. A Digital Equipment Corporation, Data General, Prime. Oh, the one California exception was Hewlett-Packard. And they were really important and interesting computers in universities. We used them, first of all, dedicated. Some people wanted a computer of their own. If you're doing interactive computer graphics, you can't share a computer and wait for your turn. Some individual units used them, would buy them and run them as small time-shared systems. Business schools, for example. And as I say, they were very good for fast computations. For the first time, small colleges and universities could afford really nice computer systems. So quite a large number of, of sort of small liberal arts colleges bought mini computers and ran small time-shared systems on them. Organization. I've mentioned the Central Computing Center. The Central Computing Center would be a center of expertise, money, and also resistance to change, okay? But mini computers naturally led themselves to departments setting up their own computers. We had at Dartmouth, the library had one, medical statistics had one, we had one in the engineering school, we had a couple centrally that we ran for special purposes and so forth. This decentralization caused some problems. Some of these problems were real. So expertise got fragmented and scattered around the place. And what you found was departments setting up expensive machine rooms. We found people always seemed to buy different types of mini computer. When I went to Carnegie Mellon in 1985, they'd recently done a survey. There were over 100 makes of computer on campus. I had no idea there were 100 people making computers. And they took the best customers away from the computer center. And computer centers didn't like losing their best customers. Businesses and universities basically responded to this challenge differently. Most commercial organizations said the computer center is in control, they make decisions about computing, and departments can't do their own thing without doing it through the computing center. And you'll find that many large organizations are still like that today, that if you go and work for them, you're going to have a, shall we say, a Dell laptop running this out-of-date version of the Windows operating system with this software. Okay. Universities allowed decentralized computing and made it work. If I survived all these changes as an administrator, it was because I early on realized you can't fight against these changes, and if you can't beat them, you better join them and pretend that you welcome them. But we tackled the problems of decentralization with some success. There's still tensions. Okay, keeping going. This is a microprocessor, okay? After a mini computer, what comes naturally next is a microcomputer. Microcomputers rapidly became called personal computers. This is an Intel 88 processor. It's typical of the processor's a computer on a chip, okay, a single chip processor, okay? And microprocessors like this and semiconductor memory, which came in the late 1970s, made it possible to build small personal computers. And from universities and education in general, the most important of the early computers was the Apple II, okay? Apple II, built by Steve Jobs and Steve Wozniak in a California garage, the correct place to start all companies. It was very popular in all types of education. If you look at this, you see there's a keyboard there. In the box with the keyboard, there is a central processor, a Motorola processor, and some memory. There's a monitor there, beginning to get some reasonable graphics, okay? Beside it, you see these two boxes here. You can't see them very clearly, but you'll see they have slots in them. And into those slots, you put things like this. This is a magnetic disk in a paper envelope, okay? They were usually called floppy disks because they were precisely that, floppy disks. And that's where you stored your data. A floppy disk like that would store a few hundred kilobytes, a few 100,000 bytes of memory. But you could take it out and you could put it back in, and you could copy, because you got two of them, you could copy and so forth. The other personal computer that was very important about that time, actually it was about 4 years later, came from IBM. It was the IBM personal computer. Here is a typical one of that time. I had one just like this. You notice it, and you probably can't see, but you see the monitor sitting on a box. And in the box, there are two of these floppy disk drives. So in this case, the floppy disk drives are built into the box, and it's got a separate keyboard. And if you can just see on the monitor what a wretchedly bad user interface these things had. And you see a personal printer. The personal printers, when they first came in, what it meant was instead of printing things out in a central machine room and having to wait for your output, you could actually have your own printer. IBM was very successful in selling these machines to the business community, They made one mistake. They didn't write their own operating system, but they contracted with a small startup by the name of Microsoft, and Microsoft eventually took over the entire business and drove IBM out of business. But there. So I said I had one of these machines, 8-bit processor, that's an Intel 1088. I had a large one with 128K of memory. That's because I wanted to be able to run a Pascal compiler. 2 floppy disks. Hard disks came in about 5 years later. You've seen the monitor, the printer. Very limited communications. There was one slow asynchronous thing you could plug in. Software, the Microsoft DOS. When I call it a crude operating system, you can't believe how crude it was or how bad the and it came with the basic programming language built in. Okay. The floppy disks were very important because they allowed a software industry to develop. The first really successful commercial application program was the first spreadsheet, Visicalc. And it really was the thing that made Apple II succeed, because the people who developed Visicalc could put it in a box with a floppy disk and a manual and sell it for, I don't know what it was, $50 or $100. And particularly with the IBM PC, but also with the Apple II, an enormous industry developed of software programs. Simple things like word processors and spreadsheets and simple databases and simple programming languages, compilers and so forth. And also quite a lot of educational applications, typically drill type applications. The Apple II was quite successful in high schools. So these were good things, but they actually caused quite a problem for universities. Remember the 3 problems we had with time sharing? Different users, we had different users. Well, different users now can have different computers. And capacity problems. If we weren't providing enough with our central computer, you could get a personal computer for your own. The total costs might be greater, but the money was coming out of individuals' pockets, not out of the university's central budget. And the programs did not have to be written locally. This, in fact, was the real reason that Apple IIs became popular at Dartmouth. I had a very early Apple II, and I did a planning model, a financial planning model using Visicalc on an Apple II with the help of a student assistant. She was brilliant. What you normally find is that the students actually spend more time with their hands on the computer than you do sitting in your office, and so they get better at the computing than I did. Anyway, the point about it was we could do that planning model much faster with the Visicalc than we could have done it on the time sharing. But there were some things which are serious, serious problems for universities with these personal computers. First of all, the user interface in the command language was terrible. By that stage, we got a pretty decent command language on the time-shared system. They were really, really slow, unbelievably slow, okay? Particularly for any mathematical calculation. You couldn't do any serious calculation. And the mainframe computers were actually quite good at those. And finally, there was no central file system. We had nowhere we could put share data, share things. They were freestanding, separate systems, and the only way you could get data from one to another was with these floppy disks. Okay, so I'm going to tell you 2 different approaches to how we solve this problem. First of all, the Dartmouth solution. Here's my 3rd picture showing a black and white picture with people with their fingers on keyboards, okay? This is actually a very early Macintosh computer. And notice the heading of this title, The Personal Computer as a Terminal. So the strategy was to encourage everybody to have their own personal computer, but to think of the personal computer as having 2 functions. One is, as a small personal computer, there were some programs that you could run on that computer, okay? You could do word processing or spreadsheets or simple graphics or things like that. But for anything more complicated, what we did was you turned the personal computer into a terminal, and the terminal connected to the central time-shared system, and then you could do what you want on the central time-shared system. At Dartmouth, we standardized on the Apple Macintosh because it was the first personal computer that had a decent user interface. Okay, it was the first personal computer that would not have been a major, major step backwards for the usability. And although there was all sorts of things wrong with the early Macintosh, that dominated our thinking. So here we have 1984, Dartmouth students taking delivery of their Macintosh computers. Nowadays, by the way, we would never use this publicity photograph like this. All publicity photographs from universities nowadays have to have the requisite number of men, women, people of various nationalities, heights, race, religion, and so forth. But in those days, we could get away with having a picture which had just 4 students. Okay, I'll skip that one. Okay. We were able to do this because having built our own time-shared system and having built our own communications network, we had a small but extremely strong technical group. Some of the best people I've ever worked with were part of that group. And we used our technical strengths, first of all, to build a campus network, and then to extend the campus network into the dormitories. We used we added the Apple networking, so-called Apple Talk, to the campus network. And we built a terminal program which ran on the Macintosh, which provided a lot of time-shared functions in a distributed way. And we created some distributed applications. In fact, these 2 applications here, a very well-loved mail program and a fetch program for file transfer, which is still widely used as a file transfer program. Some of you may have used it. And to give you an idea of where we were about 6 months ahead of Apple in deploying this. In fact, there are a lot of Dartmouth ideas, including the addressing scheme in the Apple system, when they eventually released it. By the time they released it, we had been running it for 6 months on campus and had over 1,000 active nodes. The first time I got to work with Steve Jobs personally was when we were releasing this, and he basically stripped Apple of the cables needed to connect Macintoshes to networks so that we had 700 cables when they were doing their developments on about 100 cables. And he was a person who, if you got on the right side of him, could be a good person to have on your side. Here is part of our Macintosh as a terminal. This is an early Macintosh screen dump, okay? And you see there are 5 windows there. And you notice then the first one is called D1 and the next one's D2. We actually had 2 computers running the Dartmouth time sharing in those days. U2 was a Unix computer, V1 was a VAX computer, and CMS1 was an IBM computer, okay? So here we have 5 terminal sessions going at the same time into these 5 computers. I mean, once again, by today's standards, so what, you say? In those days, to have 5 windows on the same terminal connected to 5 computers running different operating systems, this was near magic. Okay, so let's move on. Here is my 4th and final picture of somebody sitting at a keyboard, black and white, dirty grey picture, okay? This is not a Carnegie Mellon student. This is a Carnegie Mellon employee pretending to be a student for the benefit of the photographer. What he's sitting at is a personal computer, okay? It's actually an interesting computer because it's a special monitor developed by IBM specially for Carnegie Mellon and MIT. I don't think they ever released this monitor on the commercial marketplace. But the thing about this is that the computer that it's attached to, and it's actually under the desk, you can't see it in this picture, was what was called a workstation. The workstations were big personal computers that came in the 1980s, late 1980s, and they were big enough and powerful enough that almost all academic jobs could run on the personal computer, okay? So today, if I want to write a program, I write it on this computer. If I want to do almost anything that I want to do. Run, spreadsheets, databases. This is a big, powerful computer. These were the first computers that were big enough to do most of the academic work on the computer without having to rely on some central computer behind the scenes. The one on the left is a Sun 1. I never had a Sun 1. I only had a Sun 2, but I had a very early Sun 2. The one in the middle, Sun is a university. You know that Sun is Stanford University. That's what the letters Sun stand for. So the Sun 1 was actually built at Stanford for their own use and then became a commercial product. The one in the middle is a Microvax. The Microvaxes were almost as powerful as that VAX 11780, the big box that I showed you. The one on the right is a fun computer. In the mid-1980s, Steve Jobs was thrown out of Apple for being a jerk, which he was. He deserved to be thrown out. And he spent quite a lot of time visiting universities. In fact, he and I lived in the same house at one stage. And he designed and built this machine called the Next Machine, which was never a commercial success, but is actually the basis, the operating system, and this is the basis for the modern Macintosh operating system. There is a lot of Carnegie Mellon technology in this, and there's a lot of university technology in all of these machines. Most of these machines ran the Unix operating system, and I need to just say a little bit about Unix now. In particular, I need to talk about the University of California at Berkeley. Unix, which those of you who know much about the history of computer science will know, was a very, very important operating system in many, many ways, was developed at Bell Labs, research organization of the telephone company AT&T, as a time-shared computer system for mini computers. Berkeley, under the stimulus of Bob Kahn from DARPA, took the basic Unix and modernized it. They added things like virtual memory and modern operating system concepts in the so-called Berkeley software distribution. And the Berkeley software distribution, BSD 4.2, was really, really important for two reasons. First of all, it was a quite high quality, robust, modern operating system written in a programming language which made it portable and open source. Anybody who wanted to could take it. And the second thing was, it was the first operating system to have the family of protocols known as TCP/IP embedded within it. Those are the protocols for the internet that we all run today. And so here we have a portable, open source, high quality implementation of the networking protocols that became so important in future years. Almost all the early workstations ran BSD, Unix, or a variant, okay? The one exception was Digital that ran their own operating system. And the TCP/IP code was ported to almost every type of computer. And that's one of the reasons that when the internet became popular, it really took off. Okay. So what did we do? I mentioned that IBM built those workstations for Carnegie Mellon and MIT. The reason was those two universities in the early 1980s saw that these big workstations were coming and set out to build the distributed systems that you needed to use them in the university campus. And they were called the Andrew Project at Carnegie Mellon and the Athena Project at MIT. The reason we called it Andrew was not because we were founded by Andrew Carnegie, but we wanted a name that sorted before Athena in alphabetical order. You think I'm joking? I am not. It was an important criterion. Okay. But the strategy, these two projects, of course, we were rivals, but friendly rivals. But they were basically the same. Everybody has a workstation. They were expensive. They were costing about $10,000. All the workstations run the same operating system, Unix. Almost all work is done on the workstation. That's the big difference from the Dartmouth model. The workstations are connected to a high-speed network, and the network is connected to shared services such as a central file system. So you have a central file system on the network, which is why you need a high-speed network. And it's more than just a terminal. You've really got to have a high-speed network. At Carnegie Mellon, we had a research R&D outfit funded by IBM with about 30 PhD level engineers working on it for, the grant eventually was about 10 years. So this is a big commitment by IBM. And they developed graphical user interface for Unix workstations, a distributed file system, high-speed campus network, email and bulletin boards, advanced educational applications. Time sharing was withdrawn in 1978. I can't find the exact date. I don't claim personal responsibility for much of this technical work. I do claim technical responsibility for withdrawing time sharing, and I can tell you that was a very brave and daring thing to do, to become the first substantial organization, I believe, anywhere in the world that didn't have a large central computer but ran entirely on workstations. I was young and naive, and I just said, let's do it, and we got away with it. And I'm still naive. Okay, just one example. I mentioned the file system. This is the central file system, okay? From about 1987. If you notice there, what we have at the back are a series of racks, okay? Each of those racks actually is a Sun 2. It's a Sun 2 with 3 large disks. To the users, they just look like one file system. They look like a big Unix file system that you have access to from your personal workstation. Notice the operators in this picture, okay? We were very proud. We ran this machine room with nobody in it, which was another great breakthrough. This, in many ways, was the prototype for our modern server farms, where you have tens, hundreds, thousands, hundreds of thousands of small computers in a machine room, and they act as one great big file system. But the Andrew file system was the first one of this category. Okay, so this slide, you've seen something very, very similar to it before, okay? Andrew was a tremendous technical achievement. People were rightly proud of what they did, but it did not satisfy everybody. And the reason, funnily enough, were the same 3 problems that we'd had with time sharing earlier. One is one uniform service, but users are not all the same, okay? The second was never enough capacity. These machines were expensive. The file system was expensive and often, I have to say, ran a bit slowly. And we were unable to run programs that weren't written for BSD Unix, okay? Like the standard statistics packages, which we've not been able to run on time sharing. So we got the same 3 problems on the big Andrew system that we'd had on the time sharing system. The solution, and here's my solution, which some of you may recognize, is a screen dump from a Macintosh computer, or at least it was developed on a Macintosh computer. This is one of my diagrams from that period. In the top left, you see a Unix workstation, okay? Bottom left, you see the file system, and printing and mail, which were part of the Andrew project. In the middle, you see a cloud, okay? Cloud computing is now all fashionable, but we've always drawn our data networks as clouds. But there are other things on this diagram. Along the top, we've added Macintosh computers, IBM computers running DOS, VAX VMS, that's the digital computers. On the bottom, we've put some totally different systems, the library system, the administrative computers, which were sort of big minis, and the Pittsburgh Supercomputing Center. So what we've got is we've got on the left-hand side there, we've got the Andrew Unix integrated system. But here we've got all these other services over a family of protocols interchanging with each other. If you think about this diagram actually describes the computing environment that every university has today. Okay, I mean, you don't run DOS and you don't run VMS, I expect, but basically it's the principle of a data cloud, services on the data cloud, and a few types of computer. The other big exception, of course, is that many of these services nowadays are not running locally on the campus, but they're scattered around the country, scattered around the world. Okay, I knew that by this stage I'd be running short of time, but I wanted just to say a little bit about networks, okay? All of this would not have been possible if universities had not been the pioneers of mediums, of sort of organization-wide networks. I'm very fond of this picture, okay? This is from the University of Michigan, because when you're actually building a network, you've got the electronic side, you've got the protocols, you've got all the nice technical things, you've got the software, but an awful lot of the money goes to digging holes in the ground and running wires through walls. And this is a nice picture from Michigan. I could tell you about the Dartmouth network, but let me just show you one example of the situation we had in the Macintosh project. Here is an example of what you could connect to if you were a student in your dormitory room at Dartmouth, shall we say 1985 or 1986. And you can see, I'm assuming that you had a Macintosh computer. Chooser was the utility, the Macintosh utility, and you could see various printers. You can see the time-sharing system, that's Kiewit 1. You can see a file server. Can't actually see the library, but this is what the network provided. Every university was faced with this, and I think I might just talk a little bit about this book. If you look at the book, you will notice it's edited by my wife, Caroline, okay? In 1987, or thereabouts, she, for Educom, the computing organization, did a set of 15 case studies of small colleges to big universities. I think every university I've mentioned was in that book. What is your computing networking strategy? What she discovered was that of these 15 universities and colleges, 14 had said we've got to find a standard protocol to connect all these things together. We can't just live with everything being different. And they chose TCP/IP. So by that period, they'd all standardized on the protocols which we now use, TCP/IP. The 15th, by the way, was Dartmouth. And Dartmouth had built the bulk of its network before Berkeley Unix with TCP/IP came out. And they converted over quite soon afterwards. Impact of universities on networking. These were the first multi-vendor networks. IBM had an IBM network and Digital had a digital network, but these were the first multi-vendor networks. The TCP/IP code was crucial to the success of the internet. For example, MIT converted it to run on the MIT converted it to run on the IBM PC. We converted it to run on Digital's equipment. Many of the software tools that you use to manage your computers today on networks came from this period. For example, when you power up a personal computer, it goes out and finds a network address. Okay, that was actually an experimental work done at Stanford, turned into a product at Carnegie Mellon. And finally, I mentioned Cisco, which rapidly became the leading commercial manufacturer of networking equipment. They began with a stolen copy of Stanford's software and a rather bitter legal dispute with Stanford University. You can read about it if you look at the web. Okay, coming to the end. About 1990, business computing and university computing converged. And it was fundamentally because businesses adopted many of the things we'd pioneered in universities. They started using end-user computing. After fighting bitterly against the internet, they then turned around and made lots of money out of it. The people who fought most hard against the internet are the people who've made the most money out of it. That's the communications companies. The computing industry developed all sorts of super products for this world. Modern software has become too complicated. We're past the days in which a group of even 30 first-rate people can build a really major operating system. And during the late 1990s, in the so-called dot-com boom, many of the best technical staffs left universities, and universities do not have technical staffs of the ability that we had in those days to do these projects. The networking group we had at Carnegie Mellon, for example, essentially all of them went to Silicon Valley, and many of them got actually rather rich, and they deserved to. They were very, very, very knowledgeable and great people. So today, universities rely almost entirely on commercial products for their computing. And of course, they're very good commercial products most of the time. So that's the end of this period in which university computing diverged from commercial and business computing. And since my time is up, if you want to read more about this, there's some light reading. Just search on my name and the title of this talk, and you'll find an extended version. Here is my original title for the talk was From the Dinosaur to the Apple. This was a gift from IBM, okay? IBM, some people at IBM had a sense of humor. This was from a gift from an advisory board. And this was a gift for Apple. This is one of my prized possessions, a gift for Apple at the time we did the Macintosh project. So there we are. Very quick overview of what, to me at any rate, is a fascinating period of computing history, and one that's not actually been written up very much. There's an awful lot about networking that I could add in this, but you can't do everything in a short talk.